Okay, hi guys. Today we are going to talk about quiz number 7. This quiz is mostly on nucleophiles and electrophiles, evaluating a good nucleophile and a good electrophile. So let's just get started. So this first question asks us to talk about, what color are we going to use today? Let's go turquoise. So this question asks you to evaluate strongest and weakest nucleophiles out of this bunch right here. So we're looking at this bunch. So let's talk about what makes something a strong or a weak electrophile. So electrophiles are things that are electron deficient, right? That need more electron density. So carbocations are a great electrophile. But the thing that's going to make something a better electrophile, right, if we're evaluating a bunch of carbocations like it looks like we are here, the thing that's going to make something a better electrophile is having that positive charge, that electron deficiency, concentrated on one particular atom instead of spread out over multiple atoms through resonance. So let's take a look at this. This first molecule has the carbocation on one atom. This carbon is the only carbon that has a carbocation on it, or that is holding the majority of that positive charge is on that carbon. Here we could do resonance and have there be two carbons that are holding this positive charge. So this carbon also has a positive charge. So this is two carbons that are sharing the carbocation through resonance. So these are resonance structures. And then our third possibility is having there be, screw that up. Our third possibility is having there be resonance that looks like this. So again, this resonance is shared between two carbons. So before we talk about which one is the weakest electrophile, we should be able to figure out based on this which one is the strongest electrophile. The strongest electrophile in this bunch is going to be the one that has the most concentrated positive charge, the one that's delocalized the least. So I'm going to circle this one. It says to circle the one with the strongest positive charge, the strongest electrophile. So this one is going to be our strongest electrophile. And now we have to compare the bottom two as to which one is the strongest or the weakest out of those two. So honestly, there's not a huge difference between these two. Both of them have two carbons sharing a positive charge. Both of them are resonant between a tertiary carbocation and a primary, a primary allylic, so primary next to a double bond. So we have tertiary and we have primary, so we've resonated between these two. But what we're going to see here is that the type of alkene is different. So the alkene that's created here through resonance is a tri-substituted alkene. This alkene is a 4-substituted alkene. So what we really care about, this is tetrasubstituted, this is tri-substituted, well, we think about which one is more stable. Tri-substituted alkenes are actually less stable than tetrasubstituted alkenes. So in this case, this is going to be a more stable electrophile than this one. So it is going to be less powerful, I guess, as an electrophile, if you want to think about it like that. So if something is more stable, that means it's less likely to react. And in terms of electrophiles, the weaker an electrophile is, the less likely it is to react. The more stable an electrophile it is, the less likely it is to react. So in terms of here, this is the most stable, so this is the least likely to react. So this is going to be our cross-out weakest electrophile out of this bunch. So now we can move on to the next question. So the next question talks about strongest versus weakest electrophiles again, but this time it's with a carbonyl group, and so I think it's really important to talk about the most electrophilic site in this molecule first. So the most electrophilic site in this molecule is actually going to be this carbon, which kind of makes sense if you think about it, because what is that carbon double bonded to? An oxygen. And as we know full well, oxygens are electron hogs. So there's a big dipole in all of these molecules, pulling away from that top, or from the bottom carbon towards the oxygen. So that's going to make those carbons much more electron deficient than any other place in this molecule. So the carbon we're going to be comparing really is this carbon in all three examples. So we have to figure out what effect these nitrogens have on that central carbon. And what we'll find out is that because of resonance, because, again, we have these resonance structures in the nitrogen compounds where the lone pair on this nitrogen can actually donate electron density to this bond and remove electron density here. So we end up with a resonance structure, contributing resonance structure nonetheless, that looks something like this, where the positive density that is on that carbon is sort of shared by the nitrogen. The nitrogen donates some electron density, this is a bad bond, donates some electron density so that this carbon is not so needy as it would be if that nitrogen was not there to share some of the positive charge. So in terms of which one of these is going to be the strongest electrophile, i.e. that carbon, in which one of these scenarios will the carbon be most needy, most electron deficient, most reactive. All of those things sort of mean equivalent things in this scenario. So if one nitrogen is able to stabilize that positive charge, then two nitrogens will do it even better because there's a resonance structure, there's two different resonance structures possible. So two different nitrogens donating electron density to the carbon. So there's one that's the same as the one above or similar to the one above. And then there's also one that looks like this. Sorry, I forgot my positive formal charges. So now we're sharing that electron deficiency, the positive charge, over 3 atoms. So this is going to be the most stable of those, which means it's going to be the weakest electrophile, or the one that's least able to attract extra electron density. This one is going to fall right in the middle because it relieves some of that positive charge at the carbon, but not all of it. And then this one is going to be the strongest electrophile because the electron deficiency of that carbon is not able to be relieved by any resonance via those hydrogens. So it tells you to circle the one that is the strongest electrophile and cross out the one that's the weakest electrophile. So that's our second part of this question. And now we can move on to the third part of this question. So the third part of this question is again asking about electrophilicity between these 3. Now we have to identify the most electrophilic site in this molecule again, right? What do we know about boron? We know that boron is electron deficient when it only has 3 bonds, but it doesn't have a formal charge. So as of right now, all 3 of these borons appear to have an incomplete octet. Now what we're going to see is that there's resonance possible in the last example that can eliminate that incomplete octet and is actually going to show that this is not a contributing resonance structure for this compound. But first we will go through this one by one. So these fluorines, right? Fluorine we know is the most fluorine is the most electronegative atom that we have. So fluorine is going to be yanking electron density as much as possible away from that boron. There's a big electronegativity difference between boron and fluorine. So this boron is going to be extremely electron deficient. It's going to need electron density. You're stressing that incomplete octet even more than having no dipoles and just three hydrogens or 3 regular bonds. These fluorines are really, really making this a very strong electrophile. Whereas if we move down to the methyls, the electronegativity difference between a boron and a carbon, because you have to remember these are CH3s, the electronegativity difference is really not that big. It's probably half a point, I think. I don't know the numbers off the top of my head. But that electronegativity difference is not going to be big enough to pull much electron density away from the boron. Now, this is still an incomplete octet, which still makes it a pretty strong electrophile. But it's not going to be as strong as this one, which is having electron density actively pulled away from it by the fluorine. So as of right now, this is the winner so far, the top compound. And then if we look at the bottom one, we'll actually see that there's resonance possible here, such that the boron doesn't even have an incomplete octet in the contributing resonance structure. So you'll see that you can donate electron density here from the oxygen, and now you have 3 different bonds. So we have an oxygen here, this is positive, and we have 3 different places where the electron deficiency can be shared through resonance. So that positive charge, or not positive charge, but electrophilicity that is on this boron because it has an incomplete octet in this resonance structure can be shared across all 3 oxygens. And now we have a contributing resonance structure here that actually doesn't have an incomplete octet. So really the only contributing resonance structures are ones that involve this boron having a complete octet. So if you were to change, you could change it so it looks like this if you want, just like this. And then, of course, you could do the same thing with the bottom one. I won't draw it out just not to waste time. But these are the ones that are going to be contributing, and not this one. So it turns out that this is actually the weakest electrophile because it has oxygens that are donating electron density all around. So it's the least electron deficient. Whereas this guy, super electron deficient because it has fluorines actively pulling electron density away from it. Okay, now let's start with the other side of the spectrum, right, with the nucleophiles. So we're now going to evaluate which ones of these are the strongest and weakest nucleophiles. So let's talk a little bit about what makes a nucleophile strong. So what I would consider a strong nucleophile is something that has electron pairs usually, so lone pairs that are available for creating a bond, and then more electron density in general. So negative charge, extra lone pairs, things that make a nucleophile strong are things that enable it to create a bond. So lone pairs, negative charge, and then smaller sized things in general also tend to be better nucleophiles, just because there's a lot less likelihood that they'll bump into other things during the reaction. So they're very targeted when they're smaller. So those are the sort of things I would keep in mind as we work through these sets of molecules. So let's talk about which ones of these sort of fulfill those requirements that I just said. So like I said, lone pairs, negative charge are really the two things that we want to look at here. So the strongest nucleophile in this bunch is going to have something that has a concentrated negative charge. It's straight, it's streamlined, and has lone pairs to share. And so this oxygen is the one that is most willing to share its electron density as a nucleophile to create new bonds. You can see that because it has a negative formal charge, which means that it has electron density to donate. And we know that oxygen likes to have two bonds. It's most stable with two bonds. So if it can make a bond to get to that most stable neutral state, then it's going to want to do that. So this is going to be our strongest nucleophile of this set. And then in the opposite vein, something that's positive, an oxygen that's positive, an oxygen that doesn't have lone pairs to share, that's already overextending itself to share electron density, such as this guy, is going to be our weakest nucleophile because it is already overextending itself in these bonds. It already is sharing too much. It's giving too much, which means that it's not going to be a good nucleophile. It's not going to want to share anymore. So that's our first set. Fairly straightforward. Now let's look at the second set, which is this group of three right here. Now we have to talk about sort of a similar thing, but this is more about concentrated electron density as opposed to formal charge. So this nitrogen over here has a lot of concentrated negative charge, a lot of concentrated electron density. This one has some, and this one has negative charge in the form of a, not negative charge, but electron density in the form of a pi bond spread out over two atoms. So we can sort of rank these in terms of concentration of electron density. This has electron density forced onto two different atoms spread over two. This has electron density on one, but no formal charge. And this has electron density on one atom, but with formal charge. So what we're going to see is that this guy right here is our strongest nucleophile because it's small. It has electron density. It has a negative charge and an extra lone pair to share to create a new bond. This guy is going to be right in the middle, this middle one right here, because it does not have a negative formal charge, but it also still has concentrated charge on one atom. So this lone pair still makes it a decent nucleophile. And then this guy is going to be our worst nucleophile because it has electron density spread out over two carbons. It doesn't have any formal charge. It's not even a lone pair. It's a pi bond. So this is going to be our worst nucleophile. So this is going to be our weakest, and this is going to be our strongest in this set. And then finally, we can talk a little bit about the last set here. So the last set here is going to combine sort of all of those things we talked about in the first two sets. So when we talk about something being a strong nucleophile, like I've said a million times just now, we want it to be concentrated negative charge. So in this case, we have negative charge that looks concentrated at first, but we have to remember that we can do resonance, right? So that this negative charge is actually spread out over two oxygens, which is going to significantly decrease the strength of this nucleophile. So this resonance really destroys the nucleophilicity of this carbon. It's only a moderate nucleophile, and at that it's still not too good. SH, on the other hand, has a concentrated negative charge. It's small and streamlined. It's got a negative formal charge and electron density to share. So this is actually going to be our strongest nucleophile of the bunch. It's very, very strong. And then Again, we have a nitrogen with a lone pair but no formal charge. So really the comparison as to which one is going to be the weakest is going to be between this nitrogen and between the acetate. And it turns out that the lone pair on the nitrogen still makes this a decent nucleophile. It's a good nucleophile. Whereas the acetate, the spread out nature of the negative charge of the lone pair on the acetate, makes this significantly decreases the amount of nucleophilicity you can get out of this acetate ion. So it turns out that this is going to be your middle of the three, and this is going to be your weakest. So our weakest nucleophile is the acetate, and the strongest is the SH. And so let me cross this out. And those are pretty much all of the questions for this quiz. I know that one was a little bit quicker than we normally go, but I think that if you get the trends of weakest, strongest nucleophile and weakest, strongest electrophile, you're going to be much more successful when it comes to SN2 and E2 and things like that. So make yourself a list of things that make something a good nucleophile or a good electrophile, or a bad nucleophile, bad electrophile, because that'll help you when you're evaluating more important reactions in the future. So with that said, that's pretty much it for me. If you have any more questions, don't hesitate to send me an email through my Brown email or through the email associated with this YouTube account. Either one I will respond to. But yeah, good luck and happy chemming.